Now, the electronic partition function is generally fairly easy to work with, and the reason for that is that the electronic states lie massive amounts of energy above the ground state. So, if you've got the ground state here and an excited state here, you're on the order of 10 to the 4 to 10 to the 5 wave numbers. And we saw for vibrations, right, they're only on the order of 10 to the 2, 10 to the 3 wave numbers, and at room temperature, it's like some piddly fraction of per 100,000 molecules can reach those excited states. For electronic states, there's really no chance at all that they're going to be all the way up there. So almost always we can assume that QE is approximately equal to 1. And that's assuming that we've got a singly degenerate ground state. If your ground state has a different degeneracy, then if it's doubly degenerate, we would assume that the electronic partition function would be 2, and if it was triply degenerate, it would be 3. We can take something actually that's interesting. We can take sodium, and we can write an electron configuration for sodium, a neon core, and 3s1. And so this is an example of a molecule that's going to have a doubly degenerate ground state. And the reason for that is that that single electron presumably can be upspin or downspin, and since there are two possibilities, and in the absence of a magnetic field, they should have identical energies, then we might assume that the electronic partition function is 2. And if you've had some inorganic, then you should be able to come up with a term symbol for this. This is a doublet S1/2 term. Now, if you wanted to actually include the first excited state and see what the energy comes out to be, or rather what the partition function carries out to be, that's totally fine. So we can go ahead and we can draw our ground state here. So we've got our doublet S1/2 ground state here. So it's doubly degenerate. So we've said before that the partition function is going to be about 2. But there's actually a excited state. There's a doublet P0 state up here that roughly corresponds, if you like, to exciting the electron from a 3s to a 3p orbital. And the doublet P0, there's actually some terms directly above there as well. But it's on the order of about 17,000 wave numbers here. So you can look in Moore's tables actually and look up these energy levels. And it's the next one here. And we can take that into account. We can say, well, that's another place technically you could store energy. And so at room temperature, how much energy could you store up there? How accessible are these states? We can calculate the partition function. So again, Q is the sum. And if you like, we can sum over the levels. So it's the degeneracy of each level times by e to the minus the energy of each level over kT, and we can go ahead. Our ground state clearly as a value of 2 here. Why is it 2? The degeneracy is 2, and the energy we set to 0 here. So e to the 0 is 1, so 2 times 0 is 2. And then we have the next one up, so it's got a degeneracy of 2, and it's e to the minus, oh my gosh, 17,000 wave numbers. So we can multiply that by hc. We just have to make sure our c is in centimeters per second and divide by kT. And if we pick T equals 298 Kelvin, then what we find is that our electronic partition function is 2. And the second term here is 4.61, which sounds pretty good. But when you get to the next part, right, it is times 10 to the minus 36. So essentially, our electronic partition function, right, is 2.000000000, and actually you have 35 zeros in a row, and then you get to a 4. I guess in a 6 and a 1. So really saying it's 2 is really not that bad at all. You're only off when you start to go out to like the 36th decimal place. But I mean, even if you got 10 to the 23 atoms, right, you're not going to see a single atom up there unless you live for several trillion years, I suppose.